Hi everyone. Thank you for joining me at the end of Devnexus. Do you enjoy the conference? Yeah. I appreciate your presence here. My name is Koichi Sakata. I have been recognized as a Java champion and an OpenJDK committer. I'm from, do you know this flag? Here's a quick quiz. Do you know this flag? It's Japan's flag. Japan is here. It's at the top left of this map. The time difference between Japan and Atlanta is 14 hours. I finally recovered from jet lag today. However, I'm flying back to Japan. Uh-huh. Mainland, yeah. However, I'm flying back to Japan tomorrow. 2 weeks later, we have Java 1 conference. I have a talk in Java 1, so again, I have jet lag. I love trying to understand the inner workings of Java. In this session, I will cover these topics. Please hold on your questions until the end of the presentation. Thank you. First, let me explain about class files. A class file is created when you compile a Java program with the Java command. It contains necessary information for execution. For example, bytecode and the constant pool. Class files are not text files, but binary files. Here is how they look when opened with a binary editor. This is the structure of the class file. There are many items like magic, major version, minor version, flags, interfaces, fields, methods, and attributes. In this session, instead of explaining everything in order, I will focus on attributes. Attributes hold information related to classes, fields, and methods. They include code, which has bytecode within methods, local variables, and so on. Next, let's talk about the Java command. This command is commonly used to disassemble a class file. For example, if we have a class named hello world, running java-c hello world will disassemble the class and show its content. After that, we can see the bytecode. The Java command has several options, but the -c option is usually sufficient. If you want more detailed information, you can use the -v option to display additional details. There are also other options available, and you can see a list of them by using the -help option. Now, I will play a recording of the Java command in action. Let's watch the demo to see how it works. Yeah, you can see, you can use it like this. Next, let me briefly explain the reason and purpose behind discussing class files. While this session might not be immediately necessary, I believe it's a very interesting topic for developers. I've spent years gradually building this content, and it has been very enjoyable. I love talking about this topic, and while discussions about class files often focus on bytecode, I found it interesting to explore other aspects as well. That's why I organized this session. If everyone can put into practice what we've covered today, this session will be a great success. Next, let's discuss source files and class files. Source files follow the rules set by the Java Language Specification, or JLS. On the other hand, class files are regulated by the Java Virtual Machine Specification, or JVMS. Since JLS and JVMS are separate specifications, converting Java code to class file is not straightforward and requires adjustments between these two specifications. This is the role of the Java compiler. When considering the operation of the Java compiler, there are a few things to keep in mind. The first is that the compiler may create and write its own method to the class file. This excludes default constructors. The second is that the content of the generated class file can differ depending on the JDK version, even with the same source file. We'll keep these perspectives in mind as we move along this session. Next, let's talk about the methods created by the Java compiler. The compiler creates methods on its own due to differences between the JLS and the JVMS. By creating these methods, the compiler can represent the contents of Java code as class files. In simple terms, this is done out of necessity. The difference between the simple structure of bytecode and the rich expressiveness of Java code. The simple structure of bytecode and the rich expressiveness of Java code is significant. These additional methods are called synthetic methods. For example, you can see a synthetic method when using covariant return types. Let's say an interface has a value method that returns a number. The return integer class has a value method that returns an integer, which is a subclass of number. This means that the interface is implemented. By using Java on this class, you will see that the value method returning a number is also added to the interface's methods. This is to match the signature of the interface and the implementing class. Even if a method isn't written in the source file, it can be added to the class file. Next, let's briefly talk about bytecode. There are 5 types of bytecode instructions for method calls. Invoke static is for static methods. Invoke virtual is for instance methods. Invoke special is for constructors, private methods, and superclass methods. Invoke interface is for interface methods. I'll talk about invoke dynamic in detail later. This is a special instruction. Integer.value is a static method, so it's invoke static. The value method is an instance method, so it's invoke virtual. Looking at the synthetic method in return integer, we see that invoke virtual is used to call the value method you wrote. The synthetic method is created to link the value method calls together. Looking more closely, when you use the -b option with Java app to see detailed information, you will find some flags. For example, ACC synthetic indicates a synthetic method. Another flag, ACC bridge, signifies a bridge method which is created to bridge gaps between methods. A synthetic method derived from a source code definition is called a bridge method. Next, let's closely examine synthetic methods and inner classes. Inner classes can have synthetic methods generated for certain code. This was the case in JDK 10 and earlier. From JDK 11 onwards, the content of the class file has changed. Let's see how it changed. First, let's confirm what an inner class is. If there is a class named outer with a class named inner inside it, inner is the inner class. To create an instance of the inner class, you should call the constructor of inner for an instance of outer. An example of a synthetic method is when an inner class accesses private members of the outer class. For instance, if the outer class has a private method, such as mOuterPriv, it can be called from within a method in the inner class. This is possible because the inner class is a member of the outer class. We compile with JDK 10 and run the javapp command for the inner class. We can see that a mysterious static method outer data access data 000 is called. Where does the private method call go? Next, we run javapp for the outer class. The method is created by the compiler, so this is a synthetic method. It uses invoke special to call the private method. Note, it is not a bridge method. A bridge method is derived from a source code definition. This is not a case. Let's summarize things so far. Before JDK 10, a synthetic method were called in the inner class. The compiler creates the static synthetic method access $000 in the outer class. In the method, it calls mOuterPriv method. The reason synthetic methods were used is because the JVM specification did not support access from inner classes to private methods or outer classes. The concept of inner classes itself was not supported by the JVM specification. But this implementation had problems. For example, invoking reflection methods from one nested class to another could cause errors. So let's move on to the next topic, nestmates. From JDK 11, the compiler generates a different class file from this code. When you compile and disassemble the same code with JDK 11, the inner class can directly call the private methods of the outer class. In other words, synthetic methods in the inner class were no longer created, and calling private methods of the outer class from the inner class was simplified from JDK 11. To achieve this, a concept called nestmates was introduced into the class files. Nestmates defines new attributes, nest host and nest members. Nest host refers to the outer class, while nest members represents the classes nested within. By examining these attribute values, you can identify the outer class and inner classes. When using Java-B, you can see that the inner class is listed as a nested member in the outer class, and the outer class is listed as a nested host in the inner class. This makes it possible for the JVM to call private methods. The JVM specifications also introduced the concept of nesting, allowing private method calls from nested classes. This is the key point, highlighting the differences in class file content between JDK 10 and JDK 11. The main point is that the source code itself hasn't changed, but it will work the same way regardless of which JDK version you use to compile. Although users don't need to know these details, understanding these changes and the discussions around them is fascinating. Next, let's talk about changes in class file content and improvements in the JVM. Please take a look at this code. Don't worry, this is not a production code. This class has 123 string type fields. In the toString method, all of these fields are concatenated with commas. This is the main method that calls the previously mentioned toString method. It runs for 60 seconds, calling the toString method many times. The length method is called simply to make the value easier to use. Again, here is a quick quiz. What will happen if we run this code on JDK 22? Please choose from the following options. Who thinks it's option 1? Option 2? Option 3? Option 4? Thank you. That can be executed, but it consumes a lot of memory. So option 3 is correct. This issue was reported in the JDK bug system, but it was fixed in JDK 23. This is an additional note. The JVM in the OpenJDK is called hotspot VM. It has two JIT compilers, C1 and C2. C1 has a short optimized blah, 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 blah. C2 has blah, 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 blah. The hotspot VM uses both by default, which is called tiered compilation. Simply put, after a method is used a certain number of times, it is first JIT compiled with C1. And if used even more, it is JIT compiled again with C2. That's the reason why we run this code for 60 seconds. It calls the toString method many times, so the JVM compiles the toString method with C2. I actually ran this code on OpenJDK 22. I specified the memstat command in the compile command to output the memory consumption during the JIT compilation. As a result, JIT compiling the toString method consumes 1.1 gigabytes of memory and takes 25 seconds to compile. This problem does not occur in JDK 8. I have run it on JDK 8 update 401 and 8 update 275. Both versions did not have this issue. From JDK 9 onwards, this problem has arisen, but it does not occur with all string concatenations. It occurs in specific cases. When compiling literals and variables, memory consumption and compile time rapidly increase. With 3 or 4 strings, it goes unnoticed, but with 50, 100, or 123 strings, the increase is significant. There was a change related to string concatenation in Java 9. This change was the introduction of INDI, short for Invoke Dynamic Bytecode. INDI improved execution performance, although there are rare bug cases. Most cases are problem-free, but some issues can occur. We want to discuss the internal structure of string concatenation processes, but time doesn't permit today. So let's stick to the classifier theme. We will explore how it was before INDI, why string concatenation was changed, and what INDI is. First, the long concatenations in the previous test were designed to trigger the issue. Let's take a simpler example. Suppose you write code to concatenate a literal and comma to the string field F0. When you disassemble this with the java command, you will see that up until Java 8, the code used string builder to append the string and then called toString. The process itself has no issues. But since string concatenation is frequently used, there is a need to improve execution performance. In this implementation, improving performance requires changing the output of the class file. When changing to a different implementation instead of string builder, it will output a different class file than before. This also means the Java compiler needs modification. To avoid this, a method was devised to only change the JVM without needing to alter class files or the compiler. The purpose of INDI is to provide a mechanism where the method to be called is determined at runtime. Initially, INDI was introduced in Java 7 to improve performance for dynamic languages like JRuby. The method executed before the first invocation of an INDI instruction is called a bootstrap method. In Java, INDI is used in lambda expressions, string concatenation, record classes, switch expressions, and pattern matching. A bootstrap method is called when the JVM executes an invoke dynamic instruction. It retrieves the method corresponding to this INDI as an instance of the method handle class. The bootstrap method returns a call site instance that has the method handle. This occurs only for the first time. Excuse me. From the second time onwards, the JVM uses the call site to call the method when executing the same invoke dynamic instruction. With the introduction of INDI, processes that used string builder until Java 8 were simplified using a single invoke dynamic instruction. For string concatenation with ND, the class file only includes the invoke dynamic instruction, and the specifics of the concatenation process are shifted to the bootstrap method. This way, only the related implementation needs modification without changing the class file. When you disassemble a class file using invoke dynamic with java-v, the bootstrap method make concat with constants from the string concat factory is called. This is the bootstrap method. In cases where bugs occur, the string concat factory class is adjusted and fallback methods are used when many concatenations happen. Look at the inline hidden class strategy. Inline hidden class strategy replicates based on the bytecode what string builders are doing. This approach prevents excessive memory usage and long compile times. Implement efficient hidden class strategy for string concatenation. After JDK 23, C2 compilation switches to C1 compilation when errors occur. I'm not a compiler engineer, so I don't know the specifics of why the errors occur. The compile time is reduced to around 0.3 seconds, and the memory consumption is 6 megabytes. This resolves the issue. Let's look at what was achieved with Indy. Though this moves away from the core of class files, Indy has made string concatenation faster. Compared to execution times in Java 8, performance has significantly improved in most cases. Longer is faster. However, concatenating 123 strings or similar cases can show substantial increases. Despite this, improvements have continued in versions from JDK 10 onwards. To summarize the benefits and drawbacks, one advantage is that improvements can be made without changing the class file output and simply upgrading the version without recompiling applies these improvements. Additionally, using Indy makes JIT compilation more efficient compared to string builder. However, one drawback is the slight overhead introduced by using bootstrap method. From Java 9 to 13, efforts have been made to reduce this overhead. Currently, while it's slightly heavier than Java 8, the overall throughput for string concatenation has significantly improved. Unfortunately, discussing the details of these improvements is beyond the scope of today's session. However, there was a session about this topic at the JVM Language Summit in Santa Clara. For those interested, I recommend watching the recording. I watched it too, and it was very interesting. So far, we've talked about how upgrading Java versions improves overall execution performance without changing the code. Keeping Java versions updated not only enhances performance, but also improves the tools provided with the JDK. Therefore, using the latest Java version offers significant advantages. Let's wrap up. In summary, we've covered synthetic methods with covariant returns, the differences in class files before and after Java 11 with netmates, and the improvements in string concatenation with Indy. Today, I wanted to share the joy of exploring how Java works rather than just focusing on how to write code or use new features and so on. I hope you will try out what we've discussed and explore further after this session. Thank you for listening.